All right, guys, welcome to the Unit 1 Multiple Choice Part A Help video. In this video, I'm going to be going through examples that are like the problems on your worksheet, or I'll just be giving you some hints, okay? But I won't actually be doing the problems for you. This is, once again, your opportunity just to really start learning how to do some of these things on your own. So here we go. Let's go ahead and take a look at question number 1. We are given a function here. And it says, for how many positive values of b does the limit of this function exist at 2? All right, so first thing you want to notice here is that this function is a polynomial. And what's interesting about polynomials is that they are continuous. And if they are continuous, that means that the limit as x approaches b of your function should be the same thing as f of b. Okay, so if this thing equals 2, then that means f of b also equals 2. So in other words, what x value would give me a y value of 2? I guess I should put, back that up a little bit. I'm writing that. All right, so b is the x value and 2 is the y value. So when y equals 2, what does b equal? Okay, now the way we're going to do this, you'll notice on this problem that they gave us a little graphing calculator in the top corner. What you're going to do is you're going to graph this function, and you're also going to graph the flat horizontal line x equals 2. Now, if you were to graph these on your graphing calculator, the function's going to look like this for me on my problem, okay? And then if I were to graph the line y equals 2, that would go like this. Now the question on your guys' thing is asking us how many times, or in other words, how many x values have a y value of 2? Well, for me, that horizontal line of y equals 2 touches my function twice. So that means that this function here has 2 places where there's an x value that will give me a y value of 2 on my parabola. So that's how you're going to do this one. Kind of a weird question, but once again, this is all about exposing you to ideas here. So just to kind of review, since this function is a polynomial, it's continuous, and since it's continuous, the limit is the same thing as the y value. And so what x value gives you a y value of 2? Well, you can just graph it and find it. Okay, let's go ahead and take a look at question number 2. This one says a particle is moving on the x-axis, and the position of the particle at time t is given by x of t. So this says y and this is x. I'm going to change these so this is t and this is x of t. So this vertical axis represents the position of the particle and the horizontal axis represents the time. Okay, so which of the following is the best estimate for the speed of the particle at time t equals 3? Well, if x of t is the position, how can I find speed? Okay, well, speed, this is probably wasn't in our notes for the weekend, but it'll still, you'll see I'll make the connection for what we talked about in our notes. Speed is the absolute value of velocity, and velocity is the derivative of x. So the absolute value of the derivative of x is the speed. But that's not very helpful, and that wasn't in our notes anyway. So here's what I want you guys to be aware of. It's basically just what is x prime compared to x? Well, on a graph, it is the slope. And so if you want to find the quote-unquote speed of the function at any given time, you could do that by simply finding the absolute value of the slope. Okay, so let's find our slope at t equals -3. So here's where t equals -3. And what is the slope there? Now you could just do a simple rise and run. It looks like we're going over 1 and up 1 And you got to keep in mind that going to the right is a positive value and going up is a positive value. So my run is 1, my rise is 1, and therefore my speed, or my slope, I should say, is 1 over 1. And we don't really need to worry about the absolute value because it's positive. So the speed of my moving object at that point is 1. Okay. Now you can only really do that with straight lines. This green one's curving, so I wouldn't be able to ask you that right now. So there it is. That's how you'll find the speed, is you're just going to find the slope. But you want to make sure it's the absolute value of the slope, okay? Because speed is the absolute value of velocity, and velocity is the slope of the function. All right, so let's go ahead and move on to question number 3. So question number 3 says, use the table to determine for which value of x the rate of change of f of x is likely to be the greatest. Okay, now rate of change, that could be velocity, it could be speed if you want to do the absolute value of it, but those are all equivalent ideas there. But anyway, the question is asking which one of these values of t here is the rate of change the greatest? Well, the way that you would find the rate of change at t equals 4 is by taking your function, finding the derivative, and plugging in that number. Now the problem is that whenever you're doing a table, though, that's impossible. You can't do that. But what you can do is you can estimate the instantaneous rate of change, which is what this would be. I'll call that the n-rock. You can estimate that by finding the average rate of change. And the average rate of change is simply a slope formula. And so what you're going to do is you're going to pick the 2 time values that are closest to the time value that we want, which is 4, and we're going to use those instead and find the average rate of change. So here's 4, and the 2 time values that are closest to that are 0 and 6. So we're going to do f of 6 minus f of 0 over 6 minus 0. F of 6 is 500, f of 0 is 50, and 6 minus 0 is 6. And we'll go ahead and calculate that. That's 450 over 6. And we can go ahead and reduce that with a calculator here. All right, let's go ahead and write that down. That comes out to be 75. So the rate of change at t equals 4 is 75. Well, I'm just going to repeat that now for 6 and for 8. And we're going to see which one comes out to be the greatest. Now that's kind of a little bit overkill, but I'll do one more example and then I'll leave it at that. So let's go ahead and do t equals 6. So f prime of 6 is roughly the same thing as f of blank minus f of blank. We want to pick the 2 time values that are closest to 6. And so that ends up giving me 4. And then f of 8 is 900. And f of 4 is 200, and so that's going to be 700 over 4, which would be, let me calculate that real quick, 175. So as you guys can see right now, it looks like t equals 6 is bigger than t equals 4, so, but I would have to check again for t equals 8 just to be sure. All right, but I'm going to go ahead and stop there because it's just, I'm sure you guys know what to do at that point. Let's go ahead and move on to question number 4. Suppose that S of t represents the position of a moving object. Interpret what each item below represents. Now, I have worded this question different than the way it's worded on your guys' sheet, and that's on purpose. But let's go ahead and just understand this. So S represents position. So what this thing here represents is, well, the inside variable is t, right? So in that case, the 9 represents some kind of time value. So this means that at time t equals 9, the position is S of 9. So in other words, this just tells you the position at t equals 9, okay? So this one here, it's the same thing. So we have the object's position at 9 divided by 9. Now, that in and of itself doesn't really mean a whole lot. I don't know what to make of that particular thing. Something that we could do, though, is we could maybe, if we assume the following, we could maybe rewrite it like this. Maybe. Because 9 minus 0 is the same thing as 9. The only problem is this guy, s of 0. I don't know what that is, but maybe s of 9, maybe s of 0 is 0. And so we could write it like this, in which case, what this would represent is this is the average rate of change on the interval 0 to 9. Okay, so that represents an average rate of change. All right, maybe, and that's only assuming that s of 0 is 0. But without that, it kind of doesn't really represent anything, honestly. Let's go ahead and take a look at the next one here. S of 9, that's the position at t equals 9 minus the position at t equals 5. So what would that tell you? Well, if the object's located at some position at 9 and we subtract from that the object's position at 5, basically what that's going to tell you is how far the object moved over that time interval. So how far the object moved from t equals 5 to t equals 9. Okay, so this basically represents a distance. This represents a position. This represents maybe an average rate of change over an interval, but maybe nothing at all, honestly. And then what does the slope represent? Well, we talked about that before. The slope represents the velocity of the object, which is s prime. Okay? And if you take the absolute value of that, then it actually represents the speed. Okay, so there's some thoughts for you guys on what all these pieces mean. And from that, I'll let you guys go ahead and deduce the answer for 4. Let's go ahead and take a look at number 5. The confusing part of this one is the phrase that they give us here that says f of x can be made arbitrarily close to 2 by taking x sufficiently close to 0, but not equal to 0. Okay, that's a fun sentence to say. So what the heck are they saying? F of x can be made arbitrarily close to 2. That means that f of x, you could think of that as y. Y can be made arbitrarily close to, that means approaches 2 by, or we could say as, x is sufficiently close to 0, or in other words, approaches 0. Now, we've seen that kind of language in our lesson over the weekend. So look at your notes and find that kind of language, because that language exists. That means something. So this is how they're saying it on the AP exam. Oops, sorry. Technological issues here. Just a moment. Oh, we're having problems. There we go. All right. So here's how they're saying it on the AP exam, but this is how we've been saying it in class. They're just different ways of saying the same thing. So what does this mean? What did we talk about over the weekend? I'll let you guys deduce it from there. Question 6 is the same thing, so I'll leave it at that. Let's go ahead and move on to question number 7. Sketch 3 different graphs of this scenario. What this is telling me is that the limit of f of x as x approaches 2 is -4. I'm going to draw 3 different scenarios for you, and that'll help you answer your question. So on each of these scenarios, I'm going to go up to x equals 2 on the x-axis, because that's what x is approaching. Okay. Also, this is a y value. On a limit, the y value is the one that the limit actually equals. So I'm going to go down to -4 on the y-axis. Now, there's 4 ways that the limit can actually equal 4. One way is if we have an open dot here at 2 and -4, and you just have a function. Now, how you draw the function doesn't really matter, but in that case, the limit exists. the limit is -4, but in that case the function doesn't exist. But you could also draw a solid dot there. That's possible as well. In that case, the limit and the function exist at that point. All right. Another way that the limit can exist there and be -4 is if you have an open dot with your function there, and you have a closed dot, but they're just not in the same spot. In all three of these cases, we have a function whose limit as x approaches 2 is -4. So keep that in mind as you guys take a look at your question 7. All right, let's take a look at question 8. Using this graph, we're going to find each of the following. F of 0. Now this is just asking me, what does the function equal when x equals 0? Well, here's the spot where x equals 0. So what's the y value there? It's also 0. Now this is a limit. What is the limit of my function as x approaches 0 from the right side? Well, if I'm approaching that dot from the right side, what y value am I getting closer and closer to? Well, I'm getting closer and closer to the same y value we had up here at 0. But if I approach, this is a typo. Let me back out of this for a second. And I'm going to change this one to a negative. I meant that one to be a negative. There we go. But if I'm approaching at 0 from the left, what y value am I approaching? Well, in this case, I'm approaching a y value of -2. So you'll notice that the limit from the right and the limit from the left don't match. And when that happens, the limit does not exist. So that's something to keep in mind as you are doing question number 8. Let's go ahead and move on to question number 9. You're going to use a similar explanation for similar situation for 9 as we did for 8. So let's go ahead and take a look at question 10. This question is going to be helpful for about 3 problems on today's worksheet. So I put a few examples here to kind of really draw it out. So for each scenario, find the limit of your function as x is approaching 7. So here's x, and as you guys can see, 6.9, 6.99, 6.999. This is x approaching 7. And it's approaching 7 from numbers that are less than 7. In other words, it's approaching from the left. And over here we have 7.1, 7.01, 7.001. So this is approaching 7 from the right. So we'll put a little plus there. The question is, as x is approaching 7, what's the y value approaching? Because that's what we really want to know. What does the y value approach? Well, for this problem, it goes 7.9, 7.99, 7.999. So it looks like from the left side, it looks like it's approaching 8. What's it approaching from the right side? 8.1, 8.01, 8.001. It looks like it's also approaching 8. And when those two things match, that means the limit exists, and we can say, the limit is 8. Okay? Let's go ahead and take a look at the next one down here, though. Same x value, so I'm not going to change that. In all these tables that I have, all of them I'm having x approach 7, but what's happening in the y column is different. So let's take a look here. What's happening with this one? This one goes from 2 to 4.99 to 4.999. This one seems to be getting really close to 5. How about this guy? 4.98, 5.159, 5. So this one's also going to 5. Okay? So the limit must be 5. Now some of you guys might be wondering, well, Mr. Bailey, it says that y equals -8 though. You're right. What that means that this graph looks like is that means that as we're approaching from the left and right, they're both approaching the same point. But the actual y value is in a different spot. So that's one of those situations where you have a hole with a dot below it, okay? Whereas this one up here, it's just undefined. And so for that one, it really just looks like a graph with a hole in it, okay? Let's go ahead and take a look at the next one. For this one, we go to 4, to 20, to 155. Now, I want you to notice something here. These numbers are getting bigger, and they're getting bigger at a faster and faster rate. Like from here to here, it increased by 16. And then from here to here, it increased by 135. Now, if the numbers are increasing at bigger and bigger rates, as I get closer and closer to 7, they're just going to increase faster and faster. Okay? Compare that up to up here. The distance between these two numbers is 2.9. And the distance between these two numbers is 0.099 maybe? That's really small. So what's happening on this graph is as I get closer and closer to my desired value, the difference is getting smaller and smaller. So it's approaching a limit. But when the numbers are just getting bigger and bigger, what's happening is you're approaching infinity. Now the same thing is happening on this side. We go from 0 to negative 200, so it dropped by 200. And then from here to here, it dropped even more. I don't know what that would be, though, so I'm not going to try to calculate it. But it's dropping into negative infinity. Now, if both of these were positive infinity, you could say the limit's infinity. That still means the limit doesn't exist. Or if they were both negative infinity, you could say the limit's negative infinity. But that still means the limit doesn't exist. But in this case, since they're opposites, we just say does not exist. Now, what would this graph look like? Well, we have a graph, and we're approaching x equals 7. And what happens is on the left side, we're approaching infinity. So as I get closer and closer to 7, the y values just get higher and higher. And as I approach 7 on the left side, the y values just get lower and lower. And so we have a vertical asymptote situation going on with that particular table. Let's go ahead and take a look at the last one here. Here the y values go from 3.2 to 3.5 to 3.99. Looks like it's approaching 4 from the left. Here we got negative 7.1, negative 7.312, negative 7.999. Looks like it's approaching 8. So what's going on there? Well, as we approach 7, on the left side, we're approaching 4. So maybe it would look something like this. And as I approach it from the right side, we're getting up to 8. So that would look like this. So what we have in that case is a jump. And in that case, once again, we would just say that the limit does not exist in that case. So we have jumps, we have vertical asymptotes, we have holes with dots, we have holes without dots. But all those are different scenarios. The first two are ones where the limits actually existed. The last two are ones where the limits did not. So you'll see an example of those on 11 and also on 12. So hopefully that was helpful for those. Let's move on to question 13 here. We've got a piecewise function, and we're being asked to find the limit of our function as x approaches 2 with a little plus here. A plus means you're approaching from the right side of x. Now, what kind of numbers are to the right of 2? Well, that would be numbers that are greater than 2. And so we're going to use this piece right here. And so the limit as x approaches 2 from the right of f of x is going to be the limit as x approaches 2 from the right of this piece of our function, because that's where x is greater than 2. And we always try direct substitution first, and if we get an answer, then that's our answer. So if I plug in 2 for x, I get 5 times 2, which is 10, minus 8, which is 2, and there's my answer. Okay. Now, if this was a negative, I would have used the one that said x is less than. I would have used the negative 4x minus 3. All right, let's go and move on to question number 14. So I've got two graphs here, h and g, and I'm being asked to find the limit of this crazy-looking expression. Well, for this, we're just going to use our properties. Okay. I'm going to take this limit, and I'm going to apply it to the f. Let me raise my screen up here a little bit so you guys can see it. All right. I'm going to take this limit, and I'm going to apply it to the f, and I'm also going to apply it to the g. Now, whenever I find the limit for the f, I'm going to multiply it by 3. And when I find the limit of the g, I'm going to multiply that by 2. And then finally, I'm going to take those two solutions and subtract them. So let's do it. What is the limit of f as x approaches 2? Well, here's 2. And here's my y value at that point. And as you guys can see, we are approaching the same y value from the left and from the right. And so the limit exists there, and the limit is 4. So this is going to be 3 times 4. Minus, now let's do the next one, 2 times the limit of g of x as x approaches 2. So here's where x equals 2. And as you can see, whether I'm approaching from the left or whether I'm approaching from the right, they're both landing at the same spot, which has a y value of negative 1. And so now all I need to do is just calculate this. So this is 12 plus 2, which is 14, and there's my final answer. So really what we're testing here is the properties of limits. when you're taking a limit, you can just, when you're doing addition and subtraction, you can just kind of distribute that limit to both of those things. Okay, let's go ahead and move on to question 15. On this one, I'm just going to tell you what to do. Just do direct substitution. So go back to your problem and try direct substitution. You'll get the answer right away. Let's go ahead and do question 16. All right, so this is finding a limit of a rational expression that has a radical in it. And so over the weekend we talked about how to handle these. You handle it by rationalizing the function, so to speak, or getting rid of the square root where it's located. So, but before we do that, let's just kind of we always try direct substitution first. So I would plug in 11 here. Now if I plug in 11, I'm going to have 11 minus 2, which is 9. And then 9 minus, the square root of 9 is 3. And 3 minus 3 is 0. So I just get 0 on the top. And if I plug in 11 to the bottom, 11 minus 11 is also 0. Now you might think, oh boy, L'Hopital. Well, I wouldn't recommend that. I've found that L'Hopital doesn't work really well with these radical ones, and it actually just makes things messier. And so I would recommend go ahead and just use the strategy that I shared with you when dealing with radicals, and that is to multiply by the conjugate. Now the conjugate is rewriting the same thing that has the radical on it, but with one little difference. Do you see the difference? Instead of minus 3, it's going to be plus 3. So you have a radical, and then you have a non-radical number there. The sign between them is the thing that you're going to change. And so this and this are what we call conjugates of each other. And I'll explain the benefit of that in a minute. But for now, whatever you do to the top, you have to do to the bottom also. Otherwise, your fraction becomes unbalanced and you don't have an equivalent expression anymore. All right. So now let's go ahead and do this. Now, on the bottom, we're not actually going to multiply anything together. We're just going to put these expressions next to each other. But on the top, we are going to multiply. Now, typically, when you have binomials, you would need to FOIL. You would have to do the first times the first, and the first times the last. And then you would have to do the two middle ones together, and then the two outer ones together. Okay? Or the two last ones together, I should say. But here's the beauty of this process. When you have conjugates, it's much easier to multiply because most of the terms just cancel out, and the only ones that don't is the first times the first and the last times the last. So we really only need to do those two. Okay, so let's do the last times the last first. Negative 3 times positive 3 is negative 9. Next, we have square root of x minus 2 times square root of x minus 2. Now, anytime you multiply a square root by itself, you just get the same expression, but without a square root anymore. Now we can simplify the numerator a little bit. X minus 2 minus 9 is x minus 11. And that's very convenient because that allows us to do our next step, which is to cancel these out. And that's what we call removing the discontinuity. Now I'm allowed to plug in 11. That will help me plug 11 in because now that part that was making everything equal 0 is gone. And so now we have the limit as x approaches 11 of 1 over the square root of x minus 2 plus 3. And then from here we're just going to go ahead and plug in the 11. So if I do that, we can get rid of the limit because we're doing direct substitution. After you do direct substitution, you can get rid of the limit. 11 minus 2 is 9, and the square root of 9 is 3. So we end up with 1 over 3 plus 3, which is 1 over 6. And there's my final answer for that problem. Okay, so that's how you would find the limit of a rational expression with radicals in it, multiplying by the conjugate. Let's go ahead and take a look at number 17. Now, with number 17, this is a polynomial over polynomial. And in your notes from the weekend, we saw there's two ways to handle these problems. One way is by factoring. The other way is with L'Hopital's. And quite honestly, I would just recommend go with L'Hopital. So if we plug in 0, you're going to notice that we get 0 on the top, and we also get 0 on the bottom, and therefore we are allowed to use L'Hopital's rule. So L'Hopital's rule tells me that this limit is the same thing as the following limit.
take the derivative of the top. And the derivative of the bottom. Let's plug in 0 again and see what we get. That leaves me with the 4 on the top and the 9 on the bottom. I think it's a negative 9 though. And there's my answer. So L'Hopital on polynomials is a lot easier than using the factoring method. You might think, well, Mr. Bailey, why would you even bother learning the factoring method then? Well, because sometimes they phrase questions like that on the AP exam where you have to know that strategy. So, but in this case, I would say L'Hopital is a pretty nice way to go. All right, for question number 18, I'm not going to do an example. I'm just going to give you a couple of hints. First of all, L'Hopital's rule will apply. Second of all, you're going to need to find the derivative of this expression here, okay? Now, before I show you the derivative of that expression, cosine squared of x, what that really means is cosine of x squared, okay? Now, to find this derivative, you're going to do the chain rule. We have an outside function, which is the square, and then we have the inside function here, which is cosine. So when you're doing chain rule, you do derivative of the outside multiplied by the derivative of the inside. So the derivative of the outside is a power rule. So you're just going to take the 2 and you're going to multiply it to the front. So that's going to be 2. And you're going to take 1 away from the power, so it's just 1. So you don't really need to write it, and you leave the inside the same. Now we're going to multiply it by the derivative of the inside. The derivative of cosine is negative sine x. Now if I were to simplify this, the negative 1 and the 2 can come together and make negative 2. And then we can just put the cosine x and sine x next to each other. Okay? So you're going to need to know how to find that derivative, and I did that for you, so hopefully that'll be helpful. After you finish finding the limit, basically what you're going to do on this one is go through and just find the limit of all the other ones by just doing direct substitution and see which one comes out to match the answer that you got, okay, for the one that they gave you in the question. And that would be the strategy I would encourage you to try there. So that's it for this video. Hopefully it was helpful, and we'll see you guys later.